Let's actually look at what GitHub sent us by converting the response to JSON, a Python dictionary saying data equals response.json. Alright, you type google.com, the page loaded, you search something, got an answer, completely normal. But think about physics. Google servers are not in your room. They're in a data center thousands of kilometers away. You have no wire connecting to them. And yet, you just had a conversation with their computer in under half a second. How? This question is built in modern world. And the answer comes down to core engineering solutions working together. IP, so every computer has a name. DNS, so we don't have to memorize numbers. TCP, so messages don't get lost. And routing, so packets know which cables to take. Once you see how these fit together, you realize something the most programmers forget. The internet is just a massive game of passing nodes. Let's break it down. Start with the simplest problem. How do you find another computer? You need an address just like mail. To send a letter, you need a street, a city, a country. The computers have the same thing. It is called an IP address. IP stands for Internet Protocol. An IPv4 address looks like this: 142, 250, 190, 46, 4 numbers, each between 0 and 255. Around 4 billion possible addresses. Sounded a lot like the 80s. Now we're running out. So we built IPv6, the 8 groups of hex digits, practically unlimited. Enough for every grain of sand on Earth. Every device you own has an IP right now. Phone, laptop, router, smart TV. And here's the thing. Google.com is not really a name. To your computer, it's a number. It raises a question. If computers only understand numbers, how does typing google.com work at all? That is where the DNS comes in. Domain name system. Think of it as the internet's phone book. Before smartphones, you'd look someone's name up in a book to find their number. Nobody memorized raw phone numbers. You remembered the names, the book did the translation. DNS does the exact same thing for websites. You type google.com, your computer asks a DNS server, what is the IP for google.com? DNS replies with a number. Your computer connects to that number, all in milliseconds. You never see it. And here's the elegant part. DNS is not one giant computer. It's a hierarchy. Root servers know where to ask about .com. .com servers know where to ask about google.com. Google servers know the exact IP. Like asking the post office about the street, they direct you to a city office, which directs you to the neighborhood office, which knows the exact address. Without the DNS, you would have to memorize IPs for every site you visit. The modern web wouldn't exist. Okay, so now you know the addresses. You know where to send your message. But a new problem shows up. The messages you want to send might be huge. A web page, a video, an image, megabytes of data. You can't send it as one giant blob. The internet is a shared network. Millions of people are sending things at the same time. So your message gets split into small pieces called packets. A single web page might become hundreds of packets, each one numbered, each one sent separately. And here's the weird part. They don't necessarily arrive in order. One packet takes a fast route, another takes a slow route. Some get lost entirely. That is where the TCP comes in. Transmission Control Protocol. TCP is the rule book that makes sure your messages arrive correctly, completely, in right order. Here's how. Every packet has a number. When one arrives, the receiving computer says, got packet 42, thanks. It is called an ACK. What if a packet doesn't arrive, or arrives corrupted? The sender doesn't get an ACK. After a short wait, it just sends the packet again. Once everything arrives, the receiver sorts the packets by number, reassembles the original message, hands it to your browser. This is how you never notice packet loss. Your browser never shows you a half-broken page. TCP quietly resends what is needed until the message is whole. TCP is the reason why internet feels reliable. Now, one more layer. When a packet leaves your computer, how does it actually travel from you to Google? You don't have a direct cable to their data center. So, who decides the path? Routers. A router is a specialized computer. Its only job is forwarding packets. Almost every one of you have one in your home, the one that your internet provider gave you. Your packet leaves your laptop, goes to your home router, which passes to your ISP's router, which passes to the regional router, which passes to the international router. Each router looks at the destination IP, checks its routing table, decides which neighbor to hand the packet next. It's like a relay race. No single router knows the whole path. Each one just knows, for this destination, hand the packet to that neighbor. A typical packet goes through 10 to 13 routers, across continents, under oceans, through fiber optic cables, in about 40 milliseconds. Every web page you load is thousands of packets, each taking a slightly different path, routed by computers that have never met each other, reassembled perfectly on your screen. Alright, back inside VS Code, let's actually see this happen. Let's trace a real internet request right now. You're going to see every router your packet passes through. Most operating systems have a built-in command for this. On Mac and Linux, it's called traceroute. On Windows, it is tracer. It shows you every hop your packet takes. So let's try it by saying traceroute google.com. We don't have it, so we need to install it. Alright, let's say sudo install traceroute DNS util /1. Traceroute will let me see the routers, and DNS utils give me NSLookup, which we will use right after to see DNS in action. 2 tools, 1 install. So it's done, as you can see. So let's clear it. Let's run it on google.com by saying traceroute google.com. So look at this. Each row is a router, shows its IP address and the milliseconds it took to reach. First hop, my home router, then my internet provider's local node, then regional, then international, until we reach the Google's edge servers. Some hops show stars instead of numbers. That is fine, means that router didn't respond to our probe. It still passed the packet, just didn't introduce itself. All of this happens in about a second, every single time you load a page. Let's see the DNS in action. The command nslookup asks a DNS server for the IP of a domain. So let's say nslookup google.com. As you can see, there it is. That is the actual IP address of my computer uses when I type google.com, and usually you'll see multiple IPs returned. Google has servers all over the world. DNS gives you the closest one based on your location. This is global load balancing, invisibility. Every time you visit a major site, this lookup happens. Now, let's talk to the internet from inside Python. So far, we've been inside the terminal. Let's switch to a real Python script. Internet. Now, 3 lines of code, and we will talk to a server. Make a GET request to GitHub's API by saying response equal requests.get, and then let's pass in the cheese. Request.get sends a request, gets a response back. Let's print the status code first to see if it works. Let's say print, and print the content type to see what kind of data it acts. Response.headers, pass in content. Let's save it and run it by saying python internet.py. So 200 and application/JSON. 200 is the HTTP status code. Every request to a web server returns 1. 200 means success, which means, okay, here's your data. 404 means not found. 500 means the server crashed. 200 is the one you want. And the content type tells us what kind of data came back. JSON in this case, which is just a structured way of organizing text. Look at what we just did. That single line, request.get, triggered 4 things behind the scenes. 1. Python asked DNS for the IP of api.github.com. Same DNS lookup we did manually a minute ago. 2. It opened a TCP connection to that IP. 3. It sent an HTTP request, a small text message asking for the home page. 4. It waited for packets to come back, reassembled them, and gave us the response. DNS, IP, TCP, HTTP, all running in those 30 milliseconds. Let's actually look at what GitHub sent us by converting the response to JSON, a Python dictionary, saying data equals response.json. Now, let's pull a couple of values out of it by saying print data, and inside, let's say current user URL, and then let's go ahead and print data again, and let's say repository search URL. But do not forget these. Let's save it and run it again. That's the live data from GitHub servers, URLs they use to organize their API. Your computer has never met GitHub server. They don't have a direct connection, but through DNS, IP, TCP, and routing, 3 lines of Python read real-time data from the other side of the world. Now, here's why this matters today. Every AI tool you use, Cloud, Gemini, Midjourney, they all run on this exact same plumbing. There's nothing magical about talking to GPT. It is just an HTTP request. Your message gets tokenized. Remember the last video? The tokens become a JSON payload. That payload gets sent over TCP, routed across the world to OpenAI servers. The model processes it, returns the response, which travels back through the same path. Let me show you the structure. This is what every AI app on Earth does. I'm not going to actually run this. You'd need an API key, but this is the exact pattern. We already have requests imported. Now build the payload. It is just a Python dictionary. Let's say payload equals curly braces. Like we said, it's a dictionary. Say model is the key, and the value is GPT, or let's say, and then don't forget comma, and then messages. So let's say inside again the curly braces. Role user content is our message is hello. That's it. And the request is now commented out because we have no key, but this is the shape. So let's say response equals requests last, and then api.openai.com version 1 and chat and completions. Say JSON equals payload, and then finally let's say headers equal again curly braces authorization and value bearer your key. Like we said, it is not going to actually run. We need an API key, but that is the response. You see, so let's go this out. Look at this, an API URL api.openai.com, a JSON payload with the model and your message, a post request, the same library we use for GitHub. That's it. And under the hood, the same 4 steps as our GitHub hole. DNS turns api.openai.com into an API. TCP splits the requests into packets. Routers carry them to OpenAI's data center. Their servers run GPT-4 on your input, and the response comes back as more packets. Your computer reassembles them and prints the reply. AI is just the internet, passing JSON nodes back and forth. Same plumbing as 1963. Same DNS, same TCP, same routing. Just a different server on the other end. So that is the internet. IP, every computer gets a name. DNS, we use words instead of numbers. TCP, messages arrive complete. Routing, packets find their way. 4 ideas layered on top of each other, running in milliseconds every time you tap a screen. Every app, every game, every AI model you use sits on top of this foundation. And here's what's wild. Most of this was designed in 70s and 80s, before the web existed, before smartphones existed, before anyone knew what we would build on top. And it still works, because the people who designed it built it right, on simple, layered ideas. Knowing how to make an API call is useful, but understanding what happens under the ocean when you press enter is what makes you a problem solver. Next video, we go one layer deeper, the CPU. The thing that's been running all of this code the whole time. How a billion transistors actually execute an instruction. I'm Hex1000, logic behind the code. Signing out.